Hello everyone! In the previous class, we studied how to use derivatives to determine the monotonicity of functions. We know that the monotonicity of a general function is related to the positive number of its derivative function as follows. On an open interval a to b, if the derivative is greater than 0, then the function monotonically increases on that interval. On an open interval a to b, if the derivative is less than 0, then the function monotonically decreases on that interval. Therefore, we can use the sign of the derivative to determine the monotonicity of a function. So, please remember, how many methods do we have to explore the monotonicity of functions? In fact, to determine the monotonicity of a function, if it is a simple and familiar function, we can directly observe the graph of the function to make an intuitive judgment. For example, if the function y is equal to the third power of x plus 3x, we can use the graphs of y being equal to the third power of x and y being equal to 3x to intuitively determine the monotonicity of the original function. But for some functions, it seems difficult to visually judge them using graphs. For example, the function y is equal to x plus 1 of x. Among them, x belongs to the open interval from 1 to positive infinity. If everyone doesn't know the graph of this function, it seems difficult to intuitively judge the monotonicity of the original function by using the graph where function y equals x and function y equals 1 of x. At this point, we can rigorously use the definition of function monotonicity to explain the monotonicity of the original function. But for some functions, if we want to use the definition of monotonicity of a function to determine its monotonicity, some transformations even require a lot of skills. For example, the function y is equal to the third power of x minus 3x. If we want to use the definition of monotonicity of functions to illustrate, you will find some difficulties. So at this point, we can use the conclusions we explored in the previous class. Use the sign of the derivative to determine the monotonicity of the original function. In fact, the application of such functions is very extensive. Let's start exploring again. Please think about it. How can we use derivatives to study the monotonicity of functions where fx is equal to the third power of x plus the square of bx plus cx plus d, where a is not equal to 0? Let's first clarify our approach. I want to use derivatives to study the monotonicity of functions. Firstly, we need to clarify the domain of the original function. Then, through differentiation calculation, obtain its corresponding derivative function, then use the inequality solution to determine the sign of the derivative function. Thus, the monotonicity of the original function can be determined based on the relationship between the monotonicity of the function and its derivative. Here we can use an example to illustrate. Please take a look at example 1. Find a monotonic interval where the function fx is equal to the third power of 1/3 times x minus the square of half x minus 2x plus 1. Combining the ideas just now. Firstly, it can be clarified that the domain of the function is R. Then, the derivative of the function can be obtained as x squared minus x minus 2. We can factorize the equation. Get x plus 1 multiplied by x minus 2. Of course, at this point, we can separately make the derivative function greater than or less than 0. Solve two quadratic inequalities separately. But in fact, we can be more concise. Directly make the derivative equal to 0. Find the 0 point of the derivative. That is, make the derivative equal to 0. Solve that x equals -1 or x equals 2. In this way, the 0 point x of the derivative is -1 and x is 2, which divides the domain of the function into 3 intervals. We only need to determine the sign of the derivative on each interval, and the monotonicity of the function, presented clearly in a table. We can divide the table into 6 columns. The first column indicates the content represented by each row. In the first line, let's first explain the value of x. Because -1 and 2 are the 0 points of the derivative, therefore, they divided the domain into 3 intervals. We will explain in order. It is an open interval from infinity to -1, open interval from -1 to 2, and open interval from 2 to positive infinity. Next, we will explain that the derivative values can be taken within different ranges of values, because -1 and 2 are the 0 points of the derivative. So when x is -1 and x is 2, the derivative is equal to 0. And through calculations we know In the open range, from -infinity to -1, the derivative is always positive. And in the open range -1, 2, the derivative is always negative. The derivative is always positive in the open interval 2 to positive infinity. So next, we only need to use the relationship between the sign of the derivative and the monotonicity of the function to make a judgment one by one. In the open range from -infinity to -1, the function monotonically increases. On the open interval -1, 2, the function monotonically decreases. The function monotonically increases over the open interval 2 to positive infinity. Meanwhile, we can also calculate the values of the function when x is -1 and x is 2. f(-1) equals 13/6. f2 is equal to -7/3. This way, we can have a clearer understanding of the changes and positions in the function graph. So finally, answer the question. Fx monotonically increases in the open range from -infinity to -1 and from open range 2 to positive infinity, monotonically decreasing over the range of -1 to 2. We can roughly draw its image as shown in the picture. So let's sort out the problem-solving approach and process for this type of problem. In general, to use derivatives to determine the monotonicity of a function, it should be divided into the following steps. The first step is to find the domain of the function. Everyone knows that when it comes to function problems, the first step is to clarify the domain of the function. We are discussing the monotonicity of functions within the domain. Step 2. Find the 0 point of the derivative. We can first perform differentiation on the function, obtain its derivative function, and make the derivative equal to 0. The value of x obtained is the 0 point of the derivative. Step 3. Divide the domain of a function into several intervals using the 0 point of the derivative, and provide the sign of the derivative on each interval through a list, thus obtaining the monotonicity of the function over the domain. Through the table, we can clearly present the values of derivatives and the monotonicity of corresponding functions at different positions. Final answer. So, this is the general step for us to use derivatives to determine the monotonicity of a function. So, can you appreciate the characteristics and advantages of this new method of using derivatives to determine the monotonicity of functions? For example, you can appreciate the method of defining monotonicity compared to using functions. Are the characteristics and advantages of using derivatives to study the monotonicity of functions? Actually, for example, one just now, if we use the definition of monotonicity of a function to determine its monotonicity. Firstly, we can clarify that the domain of the function is R. Therefore, if x1 and x2 belong to R, and x1 is less than x2, then fx1 minus fx2 can be expressed in the following algebraic formula. And we want to discuss the monotonicity of the original function from this algebraic formula. Obviously, there are some difficulties. However, if we use derivatives to study the monotonicity of functions, we are actually transforming the original function from a cubic function to a derivative function of a quadratic function, and only need to discuss the sign of the derivative. So, this process is to transform relatively complex functions that we are not familiar with into relatively simple functions that we are familiar with, thereby simplifying our thinking and operation process. In fact, it can be seen that derivatives are a fundamental tool for studying the monotonicity of functions. This method has universality and procedurality. Derivatives can also accurately explore the changes in functions. Please think about this question. Can we explore the relationship between the speed of function addition and subtraction and derivatives? In fact, through the previous class, we went through the following research process when exploring the relationship between monotonicity of functions and derivatives. That is, observing a special case, guessing certain conclusions, and verifying them through other examples. Then explain and clarify some situations through reasoning, in order to obtain relevant conclusions. So today, let's use this research process again to solve this problem. So let's first observe some special examples and guess some conclusions. Please observe the graph of the logarithmic function y equal to ln x in the open interval from 0 to positive infinity, and consider, what is the relationship between the changes in the derivative function and the changes in the original function? In fact, for the logarithmic function y equal to ln x, we can first calculate its derivative as 1 of x, and it is known that when x belongs to the open interval from 0 to positive infinity, the derivative is always greater than 0. So based on our previous exploration, it can be concluded that y is equal to ln x and monotonically increases by 2 over the open interval from 0 to positive infinity. Meanwhile, please observe that as our value of x increases, the derivative x becomes smaller and smaller. So at this point, observe the graph of the function. You will find that the function y increases slowly as it equals ln x. The image it presents rises more and more smoothly. So from this process, we may as well boldly make such a conjecture. If the function is within a certain range, the absolute value of the derivative is small. The function changes slowly within this range. At this point, the graph of the function becomes relatively flat. Conversely, if the absolute value of the derivative of a function is large within a certain range, then the function changes rapidly within this range. At this point, the graph of the function becomes steeper. Is this conclusion correct? Let's use another example to verify. Please observe the graph of the power function y equal to the third power of x in the open interval from 0 to positive infinity. Can he verify this conclusion? In fact, for the power function y, it is equal to the third power of x. We can first calculate its derivative as 3x squared, and when x belongs to the open interval from 0 to positive infinity, the derivative is always greater than 0. Based on the previous conclusion, we know the function y is equal to the cube of x and monotonically increases over the open interval 0 to positive infinity. And as x gets bigger and bigger, the derivative 3x squared is also increasing. And observe the image. The function y equals x to the third power and increases faster and faster. The image it presents rises more and more steeply, so the power function y is equal to the third power of x, which satisfies our previous conjecture. How can we explain the relationship between derivatives and the speed of function addition or subtraction? We know that at x0, the geometric meaning of the derivative is that the function y is equal to the slope of the tangent of the graph of fx at points x0 and fx0. So, if the derivative is within a certain range, the absolute value is relatively large. This means that the slope of the tangent at each point in the function graph is relatively large within this range. And we know that near each point, the curve can be approximated by a tangent. So the final function graph presented is relatively steep. So by sorting it out, we should be able to come to such a conclusion. Generally, if a function is within a certain range, the absolute value of its derivative is relatively large. So the function changes quickly within this range. At this point, the graph of the function becomes steeper, whether upward or downward. On the contrary, the function changes slowly within this range. The graph of the function is relatively flat. We can know from this, derivatives can accurately and quantitatively characterize the variation patterns of functions. Using this conclusion, let's explore the second example. Assuming x is greater than 0, fx is equal to ln x, and gx is equal to 1 minus 1 of x. The graphs of the two functions are shown in the figure. Can you determine the correspondence between the images of fx and gx and c1 and c2? Actually, because the two functions fx are equal to ln x, gx is equal to 1 minus 1 of x. So we can take the derivatives of the two functions separately and obtain the derivative functions as 1 of x and 1 of x squared, respectively. If functions are both greater than 0 in the open interval from 0 to the infinite axis. So the original function monotonically increases over the open interval from 0 to positive infinity. So we cannot use monotonicity to determine the corresponding function. At this point, correspondence can only be made based on the speed of function addition or subtraction. Some people may have noticed that when x equals 1, the graphs of two functions intersect, and through calculations, we can know when x is equal to 1, the derivative of fx is equal to gx, and the derivative of gx is equal to 1. And further, when x is greater than 0 and less than 1, through calculation, it can be concluded that the derivative of gx is greater than that of fx, and the derivative is greater than 1. When x is greater than 1, it can be inferred through calculation that the derivative of 0 is less than gx and the derivative of fx is less than 1. So through these analyses, we can know fx and gx are both increasing functions in the open range from 0 to positive infinity. On the range of 0 to 1, the image of gx should be steeper than that of fx, and in the open range from 1 to positive infinity, the image of gx should be smoother than that of fx. So based on the above analysis, we can draw a conclusion. The images of fx and gx are c2 and c1, respectively. So the above is the content we explored in this lesson. Now let's summarize the class. In this lesson, we focused on exploring the general steps of using derivatives to determine the monotonicity of functions. Firstly, clarify the domain of the function. Then obtain its corresponding derivative function through differentiation operation, and make the derivative equal to 0. Solve for the 0 point of the derivative, and use zeros to divide the domain of the function into several intervals. Then use the list to determine the sign of the derivative on each interval. Thus, the monotonicity of the original function can be determined based on the relationship between the sign of the derivative and the monotonicity of the function. At the same time, we know that derivatives are fundamental tools for studying the monotonicity of functions, with universality and programmability. That's all for today's class. Goodbye, everyone.